So let's now have our practice problem number 3. So for our practice problem number 3, determine the safe load PU that the truss carry based on the capacity of the end diagonals, made up of double channel C12 by 30 with cover plates 200 by 10 as shown. Okay. So use A50 steel and LRFT. Okay. So for our C12 by 30, you have for C12 by 30, you have your A equal to 5,680 square millimeter. Moment of inertia along X is 67.4 times 10 to the power of 6 square millimeter to the fourth power. AY is 2.13 times 10 to the power of 6 mm to the fourth. And your centroid along X is 70.1 millimeter. Okay. Now, the total cross-section area is comprised of two channels facing each other or face to face with a distance between them. So here it's the distance. And two cover plates. So remember, this is 200 by 10. Alright. Now, the buckling will be about the weak axis. Now, the weak axis of the whole section is obviously between the X and Y axis. Now, since the weak axis is defined by the moment of inertia, we have to compute for the moment of inertia of the total cross section and compare it. Alright? Now, for the moment of inertia along x-axis, I will not be explaining how to compute for the moment of inertia. I will just show to you the whole solution. Alright? So the moment of inertia along x-axis will be 2 times quantity 67.4 times 10 to the power of 6 plus 1 over 12 200 times 10 to the power of 3 plus 200 by 10 times 305. So this is the 305 is your D. So that is the depth of the channel. I'll just write it here. So again, you have 305 plus 10 over 2 to the power of 2. So by computing the whole equation, you have for your moment of inertia along x-axis, you have 234.05 times 10 to the power of 6 mm to the fourth. Now, for your moment of inertia along y-axis, you have 2 times 213 times 10 to the power of 6 plus 5,680 quantity 250 over 2 minus 17.1 raised to 2 plus 10 quantity 200 cube over 12. Now, simplifying this, we have 149.85 times 10 to the power of 6 mm 4. Okay, comparing the values of 2, the moment of inertia along y-axis is less than the moment of inertia along x-axis. So, yung y-axis, yung moment of inertia sa y-axis yung mas maliit. Okay, so, yun yung gagamitin natin. So, before we compute for the R, so let's compute first the total area of the cross-section. So, A sub T is equal to 2 times 5,680 plus 200 times 10 quantity. So, you have here 15,360 mm squared. So, we cannot compute. Meron na tayong value for the I and meron na tayong value for the A. So, we cannot compute for the radius of variation, yung R. So, we have here R is equal to square root I, specifically IY, over A. So, that is square root over 149.85 times 10 to the power of 6 over 15,360. So, that is equal to 98.772 millimeter. Okay. So, the slenderness ratio, or your KL over R, can now be determined. So, because we have here the truss, so we can say that it's been supported to both sides. So, your K will be equal to 1.0 and your L is 5,000 millimeter. Okay? The diagonal kasi yung pinapakompute sa atin. So, your L will be 5,000 millimeter. Now, your KL over R will be equal to 1.0 times 5,000 over 98.772. So, that is equal to 50.622. So, what is our next step? Okay. Now, our next step is to determine the Euler buckling stress. So, Fe is again pi squared times E over KL over R squared. So, you have pi squared 200,000 over 50.622 squared. So, you now have 770.28 MPa. And comparing this to 0.44 times 345, which is 151.80. So, comparing this is obviously greater than 151.80. Now, therefore, the critical stress is based on the formula from inelastic buckling. So, your FCR is, of course, quantity 0.6 658 raised to 345 over 770.28. Quantity 345. So that is equal to 286.03 MPa. So again, ang instruction sa atin is use LRFD. So your phi sub c times Pn is of course 0.9 times 15,630 times 286.03 over 1,000. This will be equal to 4,023.6 kilonewton. Now, the analysis of the truss is done to determine the force of the end diagonal BE in terms of the load PU. I think I haven't written D for the truss. Okay. So let's have here force diagram for our truss. So let's say this is BE. This is your BD. And this is your R. Okay? So looking at the dimensions of our truss, we can say that the coordinates are 4, 3, 5. Okay? And based on the figure, our truss figure, we can say that our truss is symmetrical. So our R, we can say that our R is half of PU. Okay? Now, the FBD of the joint of the right support is now drawn. The equilibrium equation regarding vertical forces can now impose. So the summation of Fy is equal to 0. So 3 over 5 BE is equal to 0.5 PU. So BE is, simplifying this one, so BE is equal to 0.8333 PU. Now, after deriving the force in the end diagonal BE, this is now equated to the actual capacity of the end diagonal. So 0.833 PU is equal to 1,462.2 kilonewton. Okay, simplifying this one, we can now compute the capacity of the truss system. So the PU is equal to 162.2 over 0.8333. So that is equal to 1754.6 kilonewton. So that is our final answer. Alright?